Alright guys, slightly different format here for 4.7 transformations of quadratic graphs. I am actually going to just teach right over top of your notes. So hopefully you're following along with your notes and filling this out with me. But this should go pretty quick. So here, transformations of quadratic graphs. The first thing, the most difficult thing probably about this lesson is this idea of vertex form. But once we have things in vertex form, it actually makes graphing a quadratic very, very, very simple. And so I'll show you how that works here today. So first of all, what is vertex form? Okay, so vertex form is this form. Let me zoom in here a little bit. Is this? It's y is equal to a times x minus h squared plus k. Now, let me tell you a little bit about this. H and k are representing where the vertex is. That's why we call this vertex form. Okay, so h comma k is the vertex. So what's nice about that is there's no like if you have something in vertex form, you don't have to like do the whole negative b over 2a, figure out where the axis of symmetry is, then plug it back in to get the vertex. The vertex is actually given to you in the equation. Okay, so the vertex is going to be whatever makes this go to 0, comma, this guy. All right, so that is vertex form. And then obviously the x value of that thing, so the h value, right? So h comma k is just an xy coordinate, all right? And that x value, the h, is just going to be where the axis of symmetry is. So it's kind of like you find things backwards from what we've been doing all along. And then a determines the shape of the parabola. Okay, so if a is positive, it opens up. If it's negative, it opens down. And we're going to see like when that a is smaller than 1, like between 0 and 1, it's going to make our parabola short, fat. And if it's bigger than 1, it's going to stretch it vertically. Okay, so we're going to talk about those transformations today. All right, so example 1. Again, this will be like probably some of the hardest things you do in this homework, but it's actually not too bad as long as you remember some key things from last time and just a little bit of new from this time. So for 1a, they say to write this function in vertex form. Okay, so you got to convert from quadratic standard form to quadratic vertex form. All right, so we're going to go to vertex form. The way that we do this is this. What's cool about this vertex form is that this is just a perfect square trinomial. It comes from a perfect square trinomial, which means that we can create that within each one of these. Okay, so how can we make a perfect square trinomial? Well, we just go back to the last lesson, right? So instead of moving the 6 over, we want to keep that y there, though. Okay, so this is the part that's a little bit different, but still very similar to last time. So watch this. Here we go. Y is equal to x squared plus 4x. What I'm going to do is I'm just going to move my 6 over. Okay, I'm just going to move that over so that I have some room to complete the square here. So what I want to do is complete the square with these guys. Okay, so I'm going to take half of my middle term. Half of 4 is 2, and then square it. 2 squared is 4. So I'm going to add a 4 in. Now here's the problem. Typically, last time we would, if we added a 4 in there, we would add a 4 in on the other side. Feel free to do that, but then if we want to put it back into vertex form, we're going to have to move it back over here anyway again. So what we do instead is we kind of say, okay, here's our perfect square. The 6 is on the outside. Since I added a 4 in on this side of the equation, remember, think of an equation like a scale. If you add 4 pounds to one side, the only way to get the scale to balance again is to take it back off. Okay, so I'm going to take it back off on this side. I'm just going to do it outside of my perfect square. All right, so now this thing factors nicely. Going back to last lesson, the root of x squared is x with that sign, which is plus. The root of 4 is 2, so we have x plus 2 squared. Okay, and then 6 minus 4 is 2, so plus 2. Now we are in vertex form. That's what they want. Okay, so example 1, we're just completing the square to create vertex form. Let's do it on 1b real quick together. So here for this one, we got to take a 2 out, right? So we could just divide everything by 2, but we don't have to. Let me show you why. What I can do is split this up. So y is equal to 2x squared minus 12x. I'm going to make some room, and then I'm going to put this 17 plus 17 over here. Okay, what I'm going to do is, since I'm going to complete the square here with these guys, I'm going to just take a 2 out of both of them. So if I take a 2 out, I'm left with x squared minus 6x. Now I can complete the square. Okay, half of 6 is 3. 3 squared is 9. Okay, but here's the tricky part. I didn't just add in a 9. I added in a 9 times 2. Right? Because that 2 technically just gets distributed to everything. So even though I wrote a 9 down, it's actually 18 that I'm adding into the problem. Is 2 times 9. So what I have to do here to balance everything is I need to then subtract, not 9, but I have to subtract 18. Okay, so we still have this. Now let's simplify it. So final vertex form here would be 2 times, this thing will factor to x minus 3 squared. 17 minus 18 is minus 1. Okay, so just so I can say a couple things about this, I didn't do this on the last one, but that's okay. The vertex here will happen at, so if they ask you, like, where's the vertex of this thing? The vertex is at 3, negative 1. And this thing is being vertically stretched by a factor of 2. So we're going to talk about those transformations right now. All right, so for transformations of these things, what I encourage you to do is just hop on Desmos and graph y equals x squared, and then play with this. Play with these ideas. If we're in vertex form, it's kind of very simple to talk about what the transformations are. All of the horizontal transformations come from, remember that anything moves on a graph left and right when we have parentheses. So the only parentheses in this is the parentheses of the x minus h. Okay, so x minus h, that part of the function is going to move things horizontally. All right, it's whatever makes it go to 0. So a couple of examples. So for horizontal, what you probably want to write down in your notes is it's whatever makes this go to 0. Whatever makes this guy go to 0. Okay, so for an example, if you want to write an example down, if I have like x minus 2 squared in there, this is a shift to the right 2, because 2 would make this go to 0, so it's a positive 2, so it shifts 2 to the right. This is 2 to the right. And if you want to see it, hop on Desmos and graph it. Okay, just go y is equal to x minus 2 in parentheses squared, and you'll see that the whole parent function moved 2 to the right. Okay, if you wanted to move left, it would be x plus something. So we have x plus 1 squared. That's like 1 to the left. A negative 1 is what makes that go to 0. So negative 1 means go left 1. All right, so that's horizontal. Vertical shifts are just what happens on the outside of the parentheses. So that would be like that 2 that's up there. So if I have something like, so it's basically, as long as you can follow your notes, you can just say that this is the k value. Okay, so the vertical shift is the k value. And if k is positive, obviously it moves up. If it's negative, it moves down. So if positive, move up. If negative, move down. All right, that's the vertical shift. For reflections, this just happens if the a value that's out front, so if a is positive, then the graph opens up. That's kind of common sense. If a is negative, then the graph reflects across the x-axis. So graph would open down. Okay, so if I ask you for reflections, if they ask you for if they ask you for transformations, if you see that a parent function, the parent function is an open parabola that opens upward. So if you see a parabola that opens downward, one of the transformations would be a reflection across the x-axis. Okay, then finally we have a dilation. So a dilation just moves graphs. So like if I have a parent function, it looks like this. A dilation will either make that thing skinnier, right? So skinnier, or it'll make it fatter. Okay, so really quick, for the blue part there, if I want something vertically stretched, a vertical stretch happens when a values, if you use the absolute value of a, I guess that's better. When a values is, so when a is larger than 1. Okay, a vertical compression, so vertical, we call these things vertical because they happen outside of the parentheses. A vertical compression would be when absolute value of a. Okay, so just look at a. Doesn't matter if it's positive or negative because that's the reflection piece. But when a is between 0 and 1. All right, so we can look at a couple of those, but if you wanted to see that, you could graph, like for instance, you could graph these guys, and I'll write these down so you can play with this idea. You could graph y is equal to 2 times x minus 3 squared, and then you can also graph something like this, y is equal to 0.5 times x minus 3 squared, and see how those two things relate. For example 3 here, they want you to actually graph some of these. Okay, so for this one here, we know that the original, and I'll do this in red, the original parent function, y equals x squared, starts at 0, 0, and then we have the points 1, 1, and negative 1, 1. And then when we go to 2, if you plug a 2 into x squared, you get 4, right? So right now I'm graphing the parent function. I'm not graphing the thing that you see. But this is what we typically deal with. With a parent function, it'll be what we always deal with a parent function. So if we start there, we can now use transformations to graph this. Okay, so the transformation would be this thing is shifting 3 to the right. Okay, the vertex is shifting 3 to the right and down 2. So now we're starting here, and we can kind of follow the same pattern that we did. So from there we went over 1, up 3. Right, so over 1, up 3 would be there. Over 1, up 3 would be there. And so here would be my new graph. You don't have to draw the parent function. I'm just showing you the translations, the transformations that happened. And I say translations, you know, it is a transformation, but individually we call them translation, like how did it translate? So this thing here, if I ask you for this, and I will on the test, this will be a horizontal shift to the right 3 and vertical shift down 2. Those are your translations. Okay, for 3b here, notice here I don't have a k value out here. Okay, so the vertex happens at negative 1, 0. So it happens right here. And then from there, this thing is actually, every piece is going to be a fourth of what it was. Okay, so where I was at 1, 1, now I'll be at 1, well, if I was at 0, it would have been at 1, 1/4. So in this case, I'd be at 0, 1/4. Okay, so it's kind of like that. And then where I was at 2, instead of going up to 4, I would have been at a fourth of 4, which is at 1. Okay, so the next one over will be at 1. All right, now you can also plug in, you can make an XY table, plug a bunch of values in and get these, but I'm showing you how to do it just using the transformations, which is kind of what they encourage you to do. So this thing will be getting fatter. All right, so this is going to have a horizontal shift left 1, horizontal shift left 1, and this will have a vertical compression. Okay, and that's it, guys. If this value out in front here would have been like a 2 or something like that, then it would have been a vertical stretch. But be able to identify those things. All right, guys, that's it for this time.